Did you know that a tiny neodymium magnet, literally the size of a coin, can pull over 1,000 times its own weight? And did you know the main element inside these magnets, neodymium, Nd, is classified as a rare earth metal and is pulled out from a single massive mine in northern China that holds the biggest reserve in the entire world? These are the magnets that drive giant wind turbine rotors, power silent electric car motors, and make your smartphone even work in the first place. But here's the wild part. How can a rare metal, discovered completely by accident in 1885, suddenly become, in the 20th century, the strongest magnetic material on the planet, strong enough to crush anything that gets in its way? What secret journey does this metal go through to transform from a raw rock buried deep underground into a force so powerful that modern technology literally can't function without it? That's exactly what we're diving into today. And hey, if you like this kind of content, hit the like button and don't forget to subscribe and turn on the bell so you never miss an episode. Neodymium is a metallic element discovered by Austrian chemist Carl von Welsbach back in 1885, but its real potential didn't show up until the second half of the 20th century, when scientists developed a new type of rare earth magnet. They figured out that when you combine neodymium with iron and boron, you get magnets that are insanely strong, way stronger than old-school ferrite magnets, lighter, more compact, and perfect for shrinking electronic devices. This breakthrough completely flipped the tech world and led to essential components in electric motors, wind turbines, and almost every modern electronic device. To get neodymium, tons of rock are pulled from open-pit mines in Bayan Obo, up in northern China, one of the biggest rare earth deposits on Earth. Neodymium doesn't come in pure chunks. It's mixed in minerals like batsnasite and monazite, locked deep inside these huge geological formations. Massive drills carve deep holes into the rock. Explosives are loaded inside, and then a controlled blast tears the ground apart, breaking the rock into pieces small enough to move and process. Right after that, giant excavators scoop everything up into huge dump trucks, which haul the material straight to the processing plant. Once the rock arrives, the real work begins, a full chemical process to isolate neodymium from all the other rare earth elements and impurities. The rock gets crushed down so the minerals holding the neodymium can finally break free. Then it all gets sorted by size to prepare it for chemical treatment. The crushed ore is mixed with strong acids, like sulfuric acid, so the neodymium dissolves along with the other rare earth metals. To separate it, factories use a technique called solvent extraction, where neodymium ions get pulled out selectively through repeated cycles. After that, neodymium gets precipitated into a hydroxide, then heated until it turns into a stable oxide powder. This fine gray powder is then packed into sealed steel barrels, labeled with weight, purity, and content, and shipped out to magnet-making factories around the world. Now the real transformation begins. A sand mold is created with the exact shape needed, usually 4 cavities for 4 magnets. The tray goes into a machine that coats it with special sand. Then workers manually smooth the top to keep everything even. The tray goes back into the machine, where special gases harden the sand in just a few seconds, turning it into a solid mold with every tiny detail of the magnet's design. Next comes the alloy. The NdIb mixture, the heart of every high-power magnet, is prepared as a fine powder. It's stored under inert gas because neodymium reacts fast with air. The powders are loaded into an induction furnace with the classic ratio, 30% neodymium, 2% boron, and the rest iron. The furnace creates a strong electromagnetic field that heats the metals past 1600 degrees Celsius, melting everything into a uniform liquid inside a vacuum chamber. A must, because even a little oxygen can ruin the whole batch. Once fully melted, the glowing metal is poured into the sand molds,
each cavity filled with perfect precision. Then the alloy is left to cool. As it solidifies, it shrinks a bit, so the molds are designed with tiny compensations built in. A controlled cooling system speeds things up just enough without introducing cracks or internal stress. When the alloy has completely hardened, the sand mold is broken apart, freeing a raw neodymium iron-boron ring. At this point, it still isn't magnetic at all. The rings are loaded into a heat treatment tube filled with silica sand to distribute the heat evenly. The tube is sealed with heat-resistant cement to block oxygen, and then it's pushed into an electric furnace. Inside, the rings heat up to between 900 and 1100 degrees Celsius until they glow red hot. This step improves the internal microstructure, relieves stress, and prepares the material for magnetic alignment. Even though the rings now have their final shape, they still don't act like magnets. So while they're still hot, a strong, steady magnetic field is applied, forcing the internal magnetic domains to line up. Then comes the final punch, literally. The rings are placed inside a machine that fires a massive magnetic pulse, up to 3 Teslas, locking the alignment permanently. Now the ring becomes a fully active neodymium magnet, and at this point, it's dangerously strong. Workers have to handle them with extreme care because they can snap together with enough force to injure someone or destroy tools and electronics instantly. Since neodymium magnets corrode super easily, especially with moisture, each one gets coated with nickel. Every batch gets tested carefully, and only the magnets that hit the quality standard get approved for packaging. Finally, they're boxed inside protective cases that shield them from external magnetic fields and prevent any accidents during shipping.